Last time we started 11.1 basic notions of geometry, and we were taking a look at three-dimensional objects when we stopped off, and I believe we're here. So we talked about coplanar points being points that are in the same plane. Non-coplanar points are points that cannot lie in the same plane. You need at least 4 of those for that to actually be a possibility. And then coplanar lines are lines that lie in the same plane. And there is an image on the screen. We talked about our classroom, the lines and, or what we would imagine sort of like being lines and points on the walls and ceiling and so forth. We're going to do it with this particular diagram as well. So using this diagram, if you were looking at this and you were talking about coplanar points, can you give me, we're going to go with 4 coplanar, yeah, no, we can't do it. There's only 4 points listed in our plane. So give me, we'll do it. Start with a non-coplanar. Well, we don't have an example. How about I put one in? That's what we need. We need an extra point somewhere. So we're going to put a point right over here. We'll call it point E. And I'll put a point down here, and we'll call it point F. And then we can do it. Okay, so if I have those 2 extra points thrown in here, can you give me 4 points that are coplanar from this diagram? 4 points that all lie in the same plane. What was it?
A, C, D, and F.
A, C, D, and F. That'll work. And the plane that they lie in is the blue one that's sort of on the floor, it sort of looks like, right? How about can you give me 4 non-coplanar points? A, C, D, and E. So A, C, and D all lie in the blue plane on the bottom, but E does not. So those 4, when taken all together and considered, are non-coplanar points. Okay. And then coplanar lines. Can you give me 2 lines that are in the same plane?
A, M, and A, okay.
Okay, so you're labeling them with the letters on the letter. Okay, so what did you say, Hannah?
A, M, and A,
A, M. Oh, I know what you're, the lowercase m is the name of the line itself, so that's just line M, okay? So it's scripted in lowercase, so that line M. And what's another line?
So K.
K. So M and K. Those would be coplanar, and again, they're in the same blue plane below. If you were to want to add in lines to this or so forth, we could talk about the fact that those 2 lines, M and K, are non-coplanar with line AB, right? Because line AB would not be in the blue plane at the bottom. It would be on the back corner of this particular diagram.
How are A and D both coplanar points and non-coplanar?
And not what?
And not, like you have A and D in both coplanar?
It has to do with all 4 of them. So these 4 points all lie in the blue plane. I mean, they lie in other planes as well, but the plane they all lie in that's in common is the blue plane. There's no plane that all 4 of these, all 4 lie in. If you take them 3 at a time, they will work, but taking all 4 at a time, they don't. Yeah, good question. Okay, not only are there lines that are coplanar, sometimes we talk about lines that are skew. So specifically, if you have lines that are not coplanar, then we're going to call them skew lines. So skew lines are lines that do not lie in the same plane. So in our diagram before, we gave an example. And the one that I mentioned was line M and line AK, or AB, I don't know why is it K, line AB. Let's think about our classroom now. As we're thinking about our classroom and we're using, like we were last time, sort of the intersections of walls and ceilings and things like that as our lines. Can you see 2 lines in this room that are not coplanar? Any ideas?
Maybe. Do they have to be like an edge?
They don't have to, but you can do it with the edges, which is easier for us to sort of picture in our mind.
Because I'm picturing like if you take these bricks or whatever you call these,
Mhm.
a line on there,
Sure.
and then like one of these floor lines.
Perfect. So if you took any of these lines where the bricks are lining the wall straight across, and you could do the ceiling as well, that corner of the ceiling would work too. So any of these lines where the bricks are lining the wall, and you do the floor over here, the floor and the wall over here. So you can't do the floor and the wall at the front, because those would still be on the same wall, right? But the one over here would be different. So those would be examples of skew lines.
What about like the one on the edge of the little like cement thing
Mhm.
sticking out, and like on like the line of chalkboard?
Yep, that would work too. Exactly. That'd be another one. Yeah, so skew lines are very common. They occur all over the place. But you have to think about them a little bit carefully to make sure that you can't, in fact, draw a line through them. For example, if I did the line across the top of the ceiling over here, and I did the line across the top of the ceiling over there, they both border the ceiling. Right? They're not on the wall behind me, but they're both on the ceiling. So that one wouldn't work. Yeah.
What if you did the line up top and then the line at the bottom of this?
Yeah, those also would be coplanar.
Okay.
So if you did, that's a good example. This is the line at the top right up here, the corner between the ceiling and the wall. And if you did behind you guys, the corner between the wall and the floor, those would be coplanar. Now, we don't see that they lie on the same wall or the same ceiling, and they don't. They definitely don't. But because they're at that diagonal, they're actually still going to be in the same plane. Okay? A plane, not one of the planes that we are, seeing on our classroom physically, but it would still be lying in the same plane. All right, two coplanar lines are parallel if they do not intersect. So you guys know what coplanar lines are. They lie in the same plane. So you can draw them in a two-dimensional screen. Like I can draw them on the chalkboard, basically, if they're coplanar. And then if they're coplanar, if they're parallel and they're coplanar, then they're not going to intersect. So you're going to have your lines looking like this when you draw them out. Okay. And that works, of course, in our classroom as well, right? So, in fact, those last two that Alyssa mentioned would be parallel. Okay, they're in the same plane, right? The one that lines the top of the ceiling, the one that lines the back of the floor. They're in the same plane, A plane, this diagonal plane that's going down, but they're never going to intersect because that line up there is never going to touch the line down there at the bottom. It's not going to happen. Now, just because two lines are coplanar, of course, it doesn't always work. Our example where we had the one behind me at the top of the wall and the one over here at the top of the wall, they do intersect in that corner right over there. So those would be non-parallel lines. Still coplanar, but they're not parallel. Okay, let's do a couple examples. Can skew lines have a point in common? Why or why not? No. Leah says no.
I'm gonna ask why. I'm not interested, but I just don't think.
You don't think so? Well, you're right. They can't. Does anybody know why?
Well, they're not the same plane as my first
Mm-hmm.
so.
Yeah, they're not in the same plane. Skew lines never intersect, right? They don't intersect because they aren't in the same plane. If they were intersecting, here's the catch. Okay, so if you have a line, then a line will lie in a plane and all those points will lie in that plane, right? So you have 2 points, same plane. And then you can do the same thing with another line that's over here, right? So if you have another line that's crossing at this point right here, then those points all lie in the same plane as well. But then every point I just mentioned are in the same plane, and then they're not skew, which was the whole point. Okay, so skew lines have a point in common. The answer is no, they cannot. Because then they would be coplanar. Can skew lines be parallel? They actually can't either. Do you know why, Lacey?
If they're parallel, then something could like go between them and form a plane.
Yeah, and that's our example like we were talking about the top and the back, yeah. So there's basically 3 types of lines when we're dealing with 3 dimensions, and they're mutually exclusive. You can't be 2 of the categories. They're parallel, or they're skew, or they're intersecting. Okay? So if you have one of those categories, it's mutually exclusive. It can't include anything else that categorizes it from the other one. So the answer here is no. And again, it's the same reason, because then they would be coplanar. And again, a good example was the one that we gave with the top corner over here and the back corner at the back of the room. Okay, so if 2 points are in a plane, then the line containing them would be where? What'd you say? In that plane. Yeah, that's exactly right. So in other words, if you have 2 points that lie in the plane, then their line's going to lie in the plane. Any point between them and so forth. A line and a point not on that line determine what? Imagine the line at the top of the room behind me, okay, and then a point on the chalkboard. If you took all of that information, what would it create? A plane. Yeah, so sort of this infinite triangle, if you will, right? Because if you took 2 points on the plane up there and connected it to the point on the board, you'd create a triangle. But you have to be able to connect that point to every point on the line, right? So you'd be creating infinite, this infinite triangle shape, all in the same plane. So this would determine a plane. Two different parallel lines. It's almost funny to use the word different there, but the book did, so I left it in. Two different parallel lines determine what? A plane. Yes, they do. So if you do the parallel lines, say for instance along the top corner over here of the wall and the ceiling, and along the bottom corner of the floor and the ceiling, or the wall and the floor, you would get the plane, which is the wall, right? So these determine a plane. Even without reading it, what do you think the answer is going to be on part D? Probably a plane, but let's be careful because it could just be a trick, right? No tricks. Two intersecting lines determine what? Yeah, well, you have to be careful. It depends on how you read it, right? So they intersect in a point, correct? But they determine a plane. They would create a plane when you consider them all entirely together, they would create a plane. So they create a plane and they intersect in a point. I feel like the question there is not really clear. You probably could answer either one and make a good argument for why you said so. So they determine a point, that is, they cross in a single point. But all of those two lines taken in all their points together would create a plane.
How do they create a plane?
Yeah, so like imagine that you had, again, the line across the top of the ceiling, and you had the line from the ceiling down to the floor. Then those two lines themselves, if you take them all together, they would all lie in a plane. Yeah. So it's almost like saying when we use the phrase up here, the line on the top and the point on the board determining a plane, if you took all of those points together and combined them, they would all lie in a single plane. Yeah. I don't think the word determine there is very clear is the problem.
So,
Yeah.
so if you were to just, could that statement not be true though? Like if you have, let's say, like the board of the line of the white or the chalkboard,
Uh-huh.
and then you had another line coming down that was just. Does that make sense? Like if it's two lines that intersect each other that don't create one of the borders, is it still?
It would still be okay. So you can imagine the line across the top of the ceiling if you want, or even one of your lines that is across the bricks, and then a line coming straight down the front of the classroom. They would still create the wall, right? They would still both lie in the wall, which means they both lie in the same plane.
Okay.
Yeah, they would. All right, more about lines and planes. Two planes. Okay, so now we're talking about planes, two planes being considered at the same time. Two planes can either be parallel, where they have no points in common, or intersecting. And when they intersect in a line. So your parallel in this classroom, a really easy one would be the floor and the ceiling, right? Yeah. And if you want an intersecting one, you can take the floor and any of the walls, or the ceiling and any of the walls. And when they intersect in one of these corners that I keep calling lines, right? Yeah, that's how they'll intersect. So an example here, we'll write these down so that you have them as reference as well. An example for parallel would be the floor and the ceiling. An example for intersecting would be the floor and a wall. And when they intersect in one of those lines. It's the corners we keep referencing. Now when we compare a line to a plane, it has one of three possibilities. A line can be parallel to a plane, so each of these words or phrases go in this blank. Are you guys with me? That's what that's referencing. It's a little bit funny looking that way, but that's what it's talking about. So a line can be parallel to a plane, and if it is, that means they have no points in common. That makes sense. That's what we use when we use the word parallel. They don't have anything in common. It can be intersecting and contained inside of that plane. So it would divide the plane into two half planes. I'll give you visuals here in a second. Or it can be intersecting and not contained inside of it, sort of it punctures the plane, and it lands in only one point. Okay, so let me, instead of using the classroom picture, let's just use a sheet of paper this time. So we have a sheet of paper, right? So one possibility is we have this sheet of paper and we have a line somewhere else sort of above or below it. It has to be parallel, right? Because otherwise if I tilt it, what will eventually happen? It'll cross. Okay, so this is a parallel line and plane. Another option is that we actually take a piece of paper or a pencil and we draw something on the sheet of paper, and that would be a line in the plane, right? And then the third option is the one that I just said, what happens when we tilt it. If I tilt it, eventually it's going to cross, and when it crosses, it's going to cross at exactly one point. Can you picture that? So that's what's going on when we talk about a line and its relationship to any plane. All right, perpendicular lines and planes. Oh, you know what? There was one more thing I want to mention, this thing about half planes. If you were to create this paper, take this paper, and you drew the pencil marked line in between it, remember the paper has to go in all directions. It has to be infinite, okay? Then that line, if it were extended, and the paper, if it were extended, would cut in half. Okay, and that's what's creating the half planes, just to clarify that part of it.
Wait, can you just tell again the difference between the not contained in and contained?
Yeah, the contained in would be if I took the sheet of paper and I drew the line on the paper. Not contained in is when I have the line up above it, so to speak, but it's tilted at an angle that it eventually will cross. So it's a three-dimensional object out of space, right, and it's coming down inside of it. All right, perpendicular lines and planes. Perpendicular lines are lines that form right angles when they intersect. A line can be perpendicular to a plane if it's perpendicular to every line in the plane. And two planes are perpendicular if any angle formed by a line in one plane and a line in the other plane is a right angle. All right, so visually, you know the first one in 2 dimensions. You've seen it tons of times. In fact, the grid itself that's the backdrop of this are examples of lines that do that. Okay, so these are lines that are perpendicular. They form right angles when they cross. They do that in space, so to speak, as well, right? So if I want to take a look at the corners of our walls and so forth, this line right here and this line right here are going to be perpendicular because they form the right angle on the corner of my brick. All right, so a line can be perpendicular to a plane if it's perpendicular to every line in that plane. So let's take a look at that one. So let's say, for instance, that we have one of these vertical lines in our classroom, and we can just use the same corner that I was talking about. So if I use this same corner right here, eventually this corner hits the ceiling, correct? And when it hits the ceiling, it hits it in a perpendicular, right? I mean, because it's straight up and down. We're not leaning tower pizza here, right? We're straight up and down. And actually what happens is that every line that it hits in that plane, it's parallel, or it's perpendicular to that line as well. So if you talk about the line that's going like this, straight along this, you know, ceiling tiles kind of, you can see the right angle that it's hitting. If you can see the line that's coming out of the wall this way, it's going to hit that at a right angle. All of them it's going to hit at right angles, so it's going to be a right angle to the ceiling in general. Two planes are perpendicular if they form a right angle. So take my ceiling and take the wall. They cross it in a line, right? And it creates a right angle when they cross. You can see it, yeah? That's what that's referencing. So we would say that those planes are perpendicular. All right, so let's talk about some angles some. An angle is formed when two rays share an endpoint. So you can see my rays in the line or in the diagram below. What are the rays that are forming this angle? BA and BC, and you guys even said it right, so very well done. So the two rays in this picture below are BA, and remember you have the ray mark on top, and BC. And they share the endpoint, and the endpoint they share in this diagram is B, right? The rays are called the sides of the angle, and the shared endpoint is called the vertex. The interior of the angle is the part of the angle between the two sides, and it's the part that's shaded, that kind of orange color. That's the interior of the angle. Now, you can measure angles in multiple ways. The most common one that people tend to sort of gravitate to, or that they like the best, usually is degrees. Okay, did everybody get, I don't want to keep going, but did everybody get this one written down? Just a second. Okay. Okay. Angles are named by a number, a Greek letter. The vertex of the angle are 3 points because we need lots and lots of options apparently. I don't know why we've got all these options, but we do. So this picture right here, sometimes you'll call the angle by this Greek letter that you're seeing. So the Greek letter for this angle over here, hang on, I wanted to do that, like that, is alpha. Okay? So alpha is one of its names. You could also call it angle P. The problem in this diagram is if you call it angle P, what could happen?
I don't know if it's like the big one or the smaller one.
Yeah, there's 3 angle P's in this picture. So in this picture, calling it angle P would not be appropriate because I have multiple angle P's. I have the one that I'm talking about right here. I have one right here. It's this little one that I'm not talking about at all. And I've got this larger one over here that I'm not talking about. Those are all angle P's. So that would not be a good choice for this diagram. There is a third choice here that's pretty friendly though, and that would be to call it by the 3 angle measure or 3 points that are on there. They do need to go in order, so you would either need to say Q, P, R, or R, P, Q. P has to be in the middle because it's the vertex. Did you have a question, Hannah?
What is the first, like, is it the Greek letter?
It's a Greek letter alpha.
Okay.
Yeah.
Why would we not use that one, did you say?
It's not that we can't use it. That's totally fine for the picture that we have here. It's just only one of the options.
Okay.
Yeah. And it's fine. There's nothing wrong with that option. I don't think that's the most common way you're going to see angles labeled. Usually they're labeled by the 3 points, like we just did. That's more common of a notation. Let's see. 2 angles are adjacent if they share a common side. This one does, right? What side do they share? Yeah, ray PR, right? They share ray PR. And a common vertex, right? They share the vertex P. But they don't share any parts of their interior. You know, the rays don't overlap. So in other words, if you had a picture that looked like this, which was not drawn very well, but pretend, we couldn't talk about this ray, or angle, excuse me, and this angle being adjacent, because a portion of them overlaps in the middle. So that's not allowed if the word's adjacent. Now there's adjacent angles in my picture, right? But they wouldn't be the ones that I just marked. Okay, so no overlaps when we're talking about adjacent angles. Now let's talk about measuring angles. This is where I was headed and got a little ahead of myself. Sorry about that. The most common measure for an angle's opening is called the degree. Okay, little circle up in the middle of the air, almost looks like a superscript, or same location you would put a accent mark or a quotation mark. Because the full rotation of a circle is 360 degrees, 1 degree would be 1/360th of a full rotation. We use angle measures like this in lots of places in real life stuff. Sports is one of them. So can somebody give me an example of where you hear a degree measure used when we're talking about things in real life?
Like, well, I don't know about like gymnastics and diving, how type of rotation.
Yes, that's the one that I was definitely thinking of. So when you watch the Olympics or anything with diving, you'll hear them do a 360-degree rotation, right? Or a 720-degree rotation. And you hear it with gymnastics as well. Where else have you heard it? It doesn't have to be in sports, but that's one that I think of commonly.
Skateboarding, is that what I was thinking?
Yeah, skateboarding. Or sometimes you'll see it on the extreme sports stuff, right? With the dirt bikes and everything. Yep. There's another one that you hear it with that once I say it, you're going to be like, oh yeah.
Ice skating?
Ice skating is a good one. Yeah, you definitely hear it with ice skating. Huh?
The weather, like degree. I mean, that's a
Well, that's a different kind of degree. That's true. Not what I was thinking of. But there's another one that's the same kind of degree.
Is it a sport?
Have you ever had a car accident where your car spun? Yeah, I have. And I did a 180-degree rotation on the highway. Not what you want to do. It's definitely a bad idea. Donuts in a parking lot. Not a good plan. Okay? So anything that's rotating would be able to be used. It does use degrees often. We can break down degrees into smaller increments called minutes and seconds. So the notation for minutes looks like one little accent mark or a hash mark, and the notation for just for seconds is 2 of them. Okay, so this one almost looks like quotations. That's what they look like. When I put them into my presentation, I have to use the quotation marker for it. Okay, so you know how many minutes there are and how many seconds there are and how they're related. So let's just talk about seconds in a minute. How many seconds are there in a minute? 60. And how many minutes are there in an hour? 60. The same relationship holds for minutes in a degree. It's all about the base 60. Now, I used a word that might just have given your heart just a little bit of flutter for those of you who have taken number theory. What word did I use? Base. Yes, I did. It's a different base. It's the base 60 system. And that's what we're going to look at next. We're going to look at converting between degrees, minutes, seconds, and degrees. So, the cool thing is that the degree part never changes. So the part at the beginning that says 32 is staying 32. We don't have to do anything with it, okay? That's the cool part. The part that says 46 as a decimal point at the end is going to change. It's going to change into a number of minutes and seconds, because this one right here is all in degrees. All right, so how do we do that? Well, what we do is this. This one is already in 32 degrees. We're not going to change that. Right now we have the 0.46, and that's in degrees, and we want to turn it into minutes. And how many minutes are there in degrees? In a degree? 60. So what we're going to do is we're going to multiply it by 60. And that's going to give me a number of minutes. So what do you get when you multiply, grab your calculator if you didn't already, 0.46 times 60? Oh, who said it? Brianna, what did it say it louder for me? 27.6. So the 20, and that's minutes. The 27 is going to be what we're going to hold steady, just like the 32 was before. This is 27 minutes. But the 0.6 we're going to turn now into seconds. How do you think we're going to do that? Times 60. So what is and this is now a minute or seconds. What is 0.6 times 60? What is it?
3.6. Wait, no. Just kidding.
You're close. It's 36. Yeah, it'll be 36 when we multiply. Exactly.
Go ahead.
It's okay. You're just off by decimal, right? 36 minutes or 36 seconds. So we have 32 degrees, 27 minutes, 36 seconds. And it's all just about multiplying by powers of 60. Okay? Now that wasn't that bad, was it? Those of you who freaked out just a little bit when I said the word base. All right, now we're going to go the other direction as well. This was turning degrees into degrees, minutes, seconds. Now we're going to turn the degrees, minutes, seconds into degrees. So if we multiplied by 60 on our last example, what do you suppose we're going to do? Divide. You got it. So our 48, again, it's not changing. But each of these are going to divide it by 60, so it would be 57 divided by 60. But then there's a caveat. The 36 is not divided by 60 because it's not a number of minutes. It's a number of seconds. What does it need to be divided by? 3,600, because 3,600 is what, Alyssa? 60 times 60. It's divided by 60 squared. Because there's 60 seconds in a minute and 60 minutes in an hour. So you're dividing by 60 twice. Okay, 60 seconds in a minute, 60 seconds in a degree is what I should have said, but yeah. Okay, your calculator can help you do that, right? Absolutely. So what does your calculator tell you that 57 divided by 60 is? What was it? 0.95. Fantastic. And then what is 36 divided by 60 squared? Or 3,600? 0.01. So if we add up 48 plus 0.95 plus 0.01, what do we get? 48.96 degrees.
So is, when we were talking about the basis section number theory, so like if there was to be something that was like 1/60th of a second, then would it be like 60 to the third when you divide? Like
Yes,
how
that's
it
exactly
works.
what you would do. If there were a smaller way to increment the seconds, that is what you would do. Yeah, the process would continue. Yep. All right. Any other questions before I go to the next example? Okay. We're going to add, or this one, I use subtraction on this one. You'll do an addition one when I get in your notes, or in your homework. We're going to subtract two values, but the values are in degree, minute, second notation. Okay? I'm going to write them like you would in, first, second, third grade, where we write them on top of each other with subtraction. So I'm going to write them down as 89 degrees, 37 minutes, 24 seconds, minus 48 degrees, 57 minutes, and 21 seconds. So we're going to write it vertically, if you will. All right, so like we've done with most of the addition and subtraction you've done over your life, you start on the right-hand side, and you subtract, and there's no problem there. 24 minus 21, you can do that. What do you get? 3. So there's 3 seconds left over when I subtract. But I do have a problem on the minutes. There's 37 minutes minus 57 minutes. I'm going to need to borrow, right? So I need to take my degrees. That will no longer be 89 degrees. It'll be 88 degrees, right? I needed to borrow a degree. But how much is a degree worth? It's worth 60 minutes. So I don't have 37 here. I'm going to have 97 minutes when I borrow. And then 97 minutes minus 57 minutes would be 40 minutes. And then I can do my 88 degrees minus 48 degrees to give me 40 degrees. So I have 40 degrees, 40 minutes, and 3 seconds. Okay, so the difference is just that when you borrow, you're borrowing 60 because we're in base 60. Do you have a question, Emily?
Well, I don't know if this is possible, but like, would it be possible to where you borrow like 1 and then you can't subtract anymore? Then does that ever happen, or would you have to worry about that?
The only way that we would, if I'm understanding your question correctly, and if I'm not, just tell me again and we'll try again, is if the first number were smaller than the second one to begin with.
Right.
So we're always going to be subtracting a larger number and then minus a smaller number. So eventually you'll have enough that when you borrow, you still have enough to subtract.
Oh yeah. So then, even if it like was only 1 more, it would just be 0 degrees. It would just be.
Yes, exactly. That's true. All right.
I have a question.
Oh yes, I'm sorry, Erica.
Is it okay to leave it like that on our homework? There's not like one of the ways that you prefer it to be left
That's
in?
my note at the bottom. Yeah. So as long as your values for minutes and seconds are between 0 and 60, leaving answers in degree, minute, second format is considered simplest form for your answers. So you would stop here. Okay.
So if we have like 78 seconds, something like that, would you want us to add a degree
Yes. So when you do addition, there are going to be times when you're going to have something that's too large. So if you got an answer that gave you like 78 seconds, you'd have to turn it, you'd have to carry, is what we call it when we do an addition and subtraction with the little ones, right? You'd carry it over into the minutes column, and that 78, you'd take away 60 from it, right? And it would become 18. Exactly. And you will do some with addition that will have that feature too. Good questions. Okay. Types of angles. I know you don't have any of these drawn in yet, do you? So go ahead and sketch them in on your paper. And we're going to give names to all 4 of these types of angles. Yeah, the way these pictures differ is by how much blue they have shaded, right? So make sure when you're drawing your pictures, you do some kind of a light shading in here so that you're referencing or making sure that you have the piece that's represented in blue on the board. So remember what you call that first picture? What type of an angle it is? Right, we call that acute. An acute angle is an angle that is between 0 and 90 degrees. So this would be a picture of an acute angle. I am going to go across the top. No, we'll go down, I guess. I guess it's better. So what happens if we have a little bit bigger of an angle on the bottom left? We call that a right angle, and we've actually already referenced that when we talked about parallel and perpendicular types of lines. We're just going to go around counterclockwise apparently on my screen because the bottom right hand corner seems like the most natural place to go next. What happens if you go just a little further than a right angle? We call that obtuse. And completing our circle, if you actually, not completing the circle, but completing our circle around my diagrams, we call that a straight angle at the top. What's another name for a straight angle? A line. Which seems a little funny, right? But I mean, it works. It's called a straight angle or a line. It would be 180 degrees, exactly. So it depends on what part of it you're talking about. If you're talking about the blue shaded part, you'd be talking about the straight angle. But if you're talking about just the rays, you'd actually be creating a line. All right, our next thing we're going to look at is the circle. So a circle is a set of all points in a plane that are the same distance, that distance is called the radius, from a single point, called the center. And then an arc is a portion of the circle that can be drawn, any portion of the circle that you can draw without lifting your pencil. So let's identify that from this picture, the center. What is the center of this circle? It's O. There are infinitely many radii, or that's the plural for radius. But can you give me a couple of examples of some radii of this circle? That's close. DO would work, yeah. And it is a line segment, so we'll put the line segment notation on top of it. DO would be an example of a radius. What's another one? Okay, OA, How about OB? Is OB? Yeah, I mean, these are all examples. There's infinitely many. If you take any point on the circle and the center, it creates a radius. How about some arcs? So an arc is a portion of the circle. It's curved, obviously, and I can draw it without picking up my pencil. So if I use, let me get another color here. This piece right here would be an arc. It'd be arc AC. Now, notationally, how do I write that? Well, I write the AC, and then I write an arc on top of it like this. So not a straight piece, that's a segment. It's curved, so it's an arc. You could also talk about the arc, and this is going to sound a little bit funny, but the arc ADB. So what if I take this and I go around the other direction? Like that? That would be an arc, a really big one. Yeah.
Do you have to list all the points that you picked?
No, because there's infinitely many points.
Okay, so do you,
You have to be careful though, because if I only list AB on this one,
it goes the
you probably would have gone the other direction, right? And there's a notation for that. Each pair of points actually determines two arcs. The shorter the arc is called the minor arc, and is sometimes, and actually usually, only labeled with 2 points. So that would be the example here that we just said of AB, and it would be this piece of AB. But the longer arc is called the major arc, and it's always labeled with 3 points. Always. So if we want the major arc AB here, we could call it ADB. And it would be the one, I should have used a different color, that blue, like that. If the major and minor arcs are the same size, they're actually semicircles. So a semicircle here would be what? Can you label me, give me a semicircle? AD. AD would be a semicircle. What's that?
Would ACB be the other semicircle?
Yeah, you could label it that way, yes. So with the picture as it's drawn, yes, you could also call it ACD or ABD, either way. Yeah. All right, last slide, chord and diameter. A chord is a segment that connects 2 points on a circle. So in this diagram, AC is a chord. Now this is where it becomes really important on that notation. AC with a segment on top of it is the chord. AC with the arc on top of it is that blue arc that's located there, right? So it's the difference between this piece and this piece. That was terrible. That's better. Okay, so the arc, make sure you have the arc on top, the segment's got the segment on top. So AC with the segment on top is a chord, connects 2 points on the circle. If the chord happens to run through the center of the circle, we call that a diameter. And there's infinitely many of those. There's infinitely many chords as well. But in this picture, one of them's drawn in. What is the diameter that's drawn in on this picture right now? AD. AD would be the diameter on this particular picture. Okay, I'm going to stop this for now.